Now, for reasons that will become apparent later on, I'm going to switch to calling our function m star. But m star will have as its domain the power set of real numbers. And what does that mean? Well, something is going to be an argument to m star if it is a set of real numbers, right? Any element of the power set of the real numbers is a set of real numbers. So that just totally matches what we were saying before. So its domain is the power set of real numbers, and it will associate each set with some non-negative real number or infinity. That kind of is consistent with a possible intuition that the measure of an infinite line or ray or whatever should be infinity. But we have to build this thing, right? Defining this is not going to be completely easy, so we're going to build it up in stages. And the first stage is to sort of have the idea that if what we're trying to do is we're trying to define what m star is on any possible set of real numbers, and that set of real numbers may not have an easy and obvious relationship with any intervals, with any open-bounded intervals, then we're going to just sort of approximate it with collections of open-bounded intervals. And so that's what we're going to call a countable open interval cover of A. Hereafter, I'm going to abbreviate it with this abbreviation. If I had to pronounce it, I probably would call it c.o.i.c.o.A. I don't know. Anyway, so this, right, but the idea here is that, you know, you can take one open interval cover, right? You know, say that your example is the interval from 0 to 1. Then every one of these intervals could be the interval from 0 to 1. That would be an open interval cover. For reasons that we'll see later, it's not a great one, but that could be one open interval cover. Now imagine that you had, for instance, the closed interval from 0 to 1. Well, you could take one open interval cover that grabs everything from -1 to 2, right? Because, you know, you're going to cover this thing, then in order to capture the number 0, you're going to have a little bit more than you want on that side. And if you're going to capture the number 1, you're going to have a little more than you want on that side. But that would just be one open interval cover. That's like, so to speak, one approximation of the set by open bounded intervals. And you know, you can make all the other open intervals anything you want because you've already captured it with the first one. But anyway, you know, and then, like, you know, once you've selected that one and that's one approximation, you could select a smaller one, right? You know, maybe from like -0.5 to 1.5 or something. So anyway, hopefully that makes somewhat believable the value of defining this notion of an open interval cover as sort of approximating any given set of real numbers, right? To be a little bit more formal, what do we mean by a countable open interval cover of A? Well, to me, the easiest way to say it, right, this is not the most professional way to say it, but the easiest way to say it is that every one of these I sub j's, right, pick any j, I sub j, is going to look like this, right? It's going to have finite real numbers, right? I'm not writing all that down because I want to keep the picture simple, but it's going to have a finite real number, a sub j, and another one, b sub j, and a sub j is going to be less than b sub j. Again, I'm not writing that down just to keep the picture clean, but it's kind of intuitively obvious that that's what you would want. It's an open interval, right? I'm using parens here, and all of that makes it a bounded non-empty set, right? So if I were going to write this out professionally, I would have to sort of specify that it has to be an open, non-empty, interval, bounded, blah, right? I'd be throwing around all of these qualifications, but the less professional way is just really obvious. So I like it for that reason. But you need both, right? I mean, you got to be able to do it the unprofessional way, but also become professional when you have to. So, so that's what the intervals kind of look like. And that sort of tells us that it's countable because the index is countable and it's open and their intervals. Now, what about cover? That's this condition, right? A being a subset of the union over all the intervals makes this family of intervals a cover of A. So let's just get some exercises with this concept of a countable open interval cover. So let's take for our first example about one of the simplest examples that you could have for this. And that's the interval from 0 to 1, open. And let's sort of think this through. I mean, it's already an open bounded interval, so we could precisely cover it with the very first choice of I sub 1, right? And then you're tempted to want to just pick every other interval to be the empty set, and that's about as nice an open interval cover as you could possibly ask for. The problem is that our definition requires that none of the intervals be the empty set. And why is that? Well, we are going to want to talk eventually about the lengths of these intervals. And so we don't really want to say what the length of the empty set is right now. There's just some reasons why that's not ideal. And we don't have to, so we're not going to. So although it is a bit of a wrinkle, it's ultimately not going to matter that much. But let's just come up with another example open interval cover. So again, that should have been I sub 1, but the first one covers everything. And then we could just take I2, I3, and everything else to be the interval from 0 to 1, as I kind of discussed a moment ago. That is a valid open interval cover. It's not one that we're going to particularly like, right, because we're going to ultimately at some point be summing the lengths of these open interval covers. And if you just sum the number 1 over and over again, it goes off to infinity. So that's not ideal, but it is basically acceptable. Now, I could keep getting better open interval covers for this example. I'm going to switch to this example because it has a little bit of something that's extra interesting. And whatever we learn about here, the lessons can be exported back to this example anyway. So let's talk about this closed bounded interval. Now, I can't capture it perfectly like I could before. If I'm going to capture that 0, as I've mentioned before, I have to capture more than the 0. And if I'm going to capture that 1, I have to capture more than that, giving me a decidedly overestimate, so to speak, of my set. Now, since I have captured everything with the first one, then I'm free to choose anything I want for the remaining intervals. And I'm going to make them not empty, but also decreasing in size so that maybe these will sum together. Now, technically, as an countable open interval cover of my set, this suffices. It does the job. But it's again going to be one that we don't love because the sum over the lengths contains the harmonic series. And we know that goes to infinity. So that's not going to be a good one. Again, it's an acceptable as some open interval cover, but not the best one that we can come up with. So let's look at this next example. Now notice that this is an improvement in 2 ways. One is that I have shrank the first interval so that it has less overhang. Still some, can't be avoided, but less. So it's a kind of improvement in that way. And then over here, I have actually formed the geometric sequence, giving us the geometric series, which we know converges to a finite value. And that will be preferable, right? We'll see a little bit more on this later on. But that's also an open interval cover and even better.